On gravitational waves and precision tests. So the next speaker is LUO Yun about the project TianQin, a space-borne gravitational wave detector. Please.
Okay, good morning. Good morning, ladies and gentlemen, and it's my pleasure to have such a chance to give an introduction about our TianQin space mission. First of all, I would like to thank Professor Raymond Lefebvre to give us such a chance to me to give a talk here. The title of my talk is Introduction to TianQin. Few years ago, exactly speaking, is 2013. We have very serious discussion with a team of scientists from Sternberg Astronomy Institute, Moscow State University, talk about the possible space mission to detect a gravitational wave. And finally, after 2 years study about this concept of space mission, we submitted our paper to the classical quantum gravity on September 1st, 2015, just about 13 days before the LIGO get the first gravitational wave signal in that time. So this is some a little bit different. Really lucky for us to propose such idea before that. My talk includes several parts. The first is a very brief background introduction about the gravitational wave, and the few parts, 3 parts is an introduction about the TianQin, and finally we want to find the possibility to cooperate with the college in the international range. As we know, about 100 years ago, the Einstein formulated such a formulation, and it's so-called general relativity. And this equation, in the left is the geometry is a curve, and the right hand is the energy or the momentum of the mass. So just as John Wheeler put it as that, the space-time tells matter how to move, and the matter tells space how to curve. And not so long later, the Einstein himself find a solution about his formulation, and this is a so-called gravitational wave solution. So this is very important. As we know that now the gravitational wave have 2 polarization and propagate with the light of the speed of light. So this is the most important features of the gravitational wave. And after light, a lot of experiments have been tested this theory, and such as orbit precision of Mercury, and deflection of light by sun, gravitational redshift, and also Shapiro delay, flame charging, and the gravitation length. And at last, in 2015, gravitational wave was discovered by the LIGO group. This we find the last losing segment of the theory, or the picture, or the puzzle. This is very important. So right now we can think this picture is a complete complexion. And why we wait so long to find the gravitational wave? This is very, very difficult because the gravitational wave effect is so teeny, so small to find. It's very, very difficult for the experiment. For example, for the typical strengths of gravitational wave in what have been discovered by the LIGO system first. In the first event detected by the LIGO, 2 black holes as much as 29 mass of sun and 36 mass of sun emerge at about 13 billion light years away, producing a gravitational strain on the Earth is at the order of 10 to minus 21. What is this effect? This factor is as big as that. Just changed a little bit between the sun and the Earth size of atom. So this is very, very teeny, so very, very difficult. So the challenge of detection of gravitational wave is extremely challenging compared with any other precision experiment. The importance of gravitational wave is, as we know, at least in 2 directions, two sides. The first of all is a new method for the astronomy observation. As we know, right now, all the astronomy observation is depends on the optical, electromagnetic, or wave, something like light. But once we have technology of gravitational wave detection, we open a new window. Because in this case, we can observe our universe with another method. This is a multi-messenger arrow. So with this method, we can hear something happening in our universe. The second one is we can test gravitational wave at extreme conditions. So what we have observed by the LIGO is the marriage of black holes, something like that, is very, very extreme conditions. In this case, we can test of gravity, the property of gravity, and we can also test for the correction of gravitation, general relativity is very, very important. And also we can use it to find a lot, maybe on foreseen physics. And as we know, everybody knows maybe much better than me because I'm not an astronomy, I'm a physicist, and exactly speaking, I'm an experiment. So after LIGO discovered in 2015, we have get successful in the astronomy physics here, and because LIGO have already brought new discovery in astronomy here, mentioned something about that. And why, after LIGO have tested the signal of gravitational wave, we need to do such things in space. Because the Stephen Professor Vitana have gave a very, very good explanation about that. So from this picture, we can see a lot of events, a lot of sources, just in the band of much lower than the band which have been performed by the LIGO. So in this case, in this millihertz frequency band, have the most predictable and the most powerful GW sources, but which is not accessible to the terrestrial detector. So even for the new devices, new projects such as Dragfree, the bandwidth is also limited. So that is why we're trying to push forward the space the space-based gravitational wave detection net. The principle is almost the same for the space-based gravitational wave detector as the LIGO, the ground-based detector. So here is the laser interferometer, and then this triangle is a equilateral triangle. This configuration just like this one, but once we have additional links between the satellites, so this is redundant for us. So we can get much more, not much more, we can get residue signal from this system. This is much more confidence for our final result. Of course, we will use also in principle of laser interferometer, but sometimes a little bit different because the distance between the satellites is far away. We need to use some response or time delay interferometer, something like that. So we need the phase locking technology and something like that. It's quite different from the LIGO. And here is the LISA, which has been introduced by the Vitala quite well. So just list some key properties here, characteristic here. This is the current ESA lead project. The armlength light is 2.5 million kilometers between the spacecraft. Expected launch time is 2034. I'm not sure, maybe earlier, maybe later, something like that. The distance to the Earth is 50 million kilometers away because they're afraid of a factor of the Earth itself. That is sometimes is a problem for us for the space-borne experiment. And also the transfer time is a little bit longer compared with other space mission because these are far away from Earth. We need to wait a long time. And the data downlink is not so big. Yes. And what is the basic idea about TianQin? Because as gravitational wave observatory, we need to concede. The first, it's easy to deploy and operate. If it's too difficult, we will risk seriously. So the second, can we achieve a larger part of LISA size? This is what question we ask ourselves. So we need to think about that. The first one, I think, we need our geocentric orbit choice. And the second one, we need to, the armlength of our triangle is comparative with the LISA. That is the two choices. So the preliminary conception of the TianQin is like that. So we also have three satellites in equilateral triangle formulation. This is usually what we have mentioned, the advantage of this triangle formulation. This is very important. And the second one is concentric orbit. The radius or the distance from the Earth is about 10 to power 5 kilometers away. And this is compared with the DCIGO is 50 times higher than that. The third one, the orbit plane is phase. The RX-0806 is a little bit far away from this one. You see, this is a bilateral system. And what has been observed by the astronomy quite well, we know some properties quite well. So I need to explain why we find this one at first, because in the 2013, once we discussed the space mission of the gravitational wave with our friends that come from Moscow State University. In that time, the gravitational signal was not discovered. So it is possible for us to test gravitational wave, general relativity as soon as possible, as simple as possible. That is what our motivation first. So we design this configuration face to these sources, these gravitational wave sources. So this is very important because this constellation is comparatively easy with LISA to realize. So that is our first motivation. So we continue to do something about that. We hope to find the possible orbit for us to realize this idea. And because the distance, you see, because the distance between the two satellites is not so short compared with the arm length of the LISA, so the frequency band is a little bit shifted from the left to the right. So in this means, the most part of science studied by the LISA can be realized in our TianQin space mission, if possible. So this is the most important. So Stefano have explained a lot of science of gravitation of the LISA. Here we will not repeat again about that. This is what have been discussed by Veitala already. So, and also some more detail with our TianQin capability that. So this one have been already discussed in our paper in the classical quantum gravity already in 2015. And here I need to emphasize some special features of TianQin. First of all, first difference, the remarkable difference between our TianQin and LISA is our orbit is a geocentric orbit, and LISA is a heliocentric orbit, because this is the most difference. And the second one, I will explain what it means standing the constellation plane, because our system is not in this elliptic orbit, but in the vertical direction. That is different compared with some proposal before, such as Omega, something like that, LIGO, something like that. And also we have some strategy about 3+3 observation schedule, because in our design, there are 3 months. Each 3 months cannot be operated because the sunshine will go directly through our telescope. That is very important. So this is a comparison between our TianQin and LISA. This is a LISA. So this is arm length. And the arm length in our system is 170,000 kilometers away, and not 2.5 million kilometers away. Here is a geocentric. You see, these 3 satellites go around the Earth, and it is about 100,000 away from our Earth, and this is a geocentric orbit. Here is another one. And of course, our design have some advantage compared with LISA. For example, the transfer time is much shorter compared with the LISA, because LISA go far away from our Earth, so there's some difficulties. And also the data down link is some advantage of it, but I think this is not so important, because for the LISA and for any space-based gravitation detector, there is no so big data need to be transferred. So download. So that is not so important. But I think mycology knows one advantage that is important, because we can, by means of the laser range, we can help us to form the constellation. That is very important. And also some disadvantage about that. That is the sensitive mechanical environment just mentioned. We have discussed with Vitala, and we have already estimated about this effect in our system is not so important. But if lower the orbit, it will be much bigger problem. And also, we need to consider sunlight and the thermal environment, and that is quite important. So the question is that existence of suitable or geocentric orbit, that is worry about. In this orbit, in this height, where it's possible to find such orbit, is certified three key crucial conditions. The first is a distant change. It's very small. The second is a relative speed is very small. Otherwise, we have faced the Doppler shift effect about that. And also the angle between the two lines will be kept constant already also. So we are lucky we find the orbit like that. And but finally, not only one orbit like that, and several or many orbiters is possible to find. We have found that one. So in this case, compared with the original geocentric orbit proposed by some people, and ours are just different because we stand on that, such like that. So this is 5 degrees lower than this orbit. And in this case, we just in the vertical direction. That is quite different. In the following proposal, is like just in the same plane, so it cannot be operated. And this is artist's illustration about that. It is also something like that. So here is a so-called 3+3. In these 3 months, we can operate this system, but in this direction we cannot, because the sunshine will be directly destroy the observation of telescope. And then another 3 months we can operate it, so stop 3 months, something like that. And also this is some design about our satellites. And the key technology have been mentioned, I think, by the first speaker, Vitala. They're almost the same. And everything, I think, is a common technology and some key what we needed to improve. And this is something we have mentioned about that. Here you will find the residual acceleration on the Tesla mass is 10 to minus 15, something like that. Yeah. And also we need the inertial sensor, the macro thruster, and the thermal fluctuation. That is very. And also this design, the inertial sensor. And we have started this work after last grassroots meeting. I met with Lofeli, and once I come back, I try to get a grant. So this was started in 2001. So we have already launched twice already to check our inertial sensor. And this is a group of inertial sensor group in our Huazhong University of Science and Technology in Wuhan. I was there, worked there for more than 30 years. And also laser interferometer, we have already get, this is a requirement, and we have already get a result in our laboratory. This is the laser, the space laser interferometer design, and we have already get some result. And in the laboratory level, it has been reached at picometer sensitivity already. And this is a group. This guy comes from Taiwan, the Professor Xianji Ye. He is absent this time. And also, we're trying to go to the satellites and the consideration about that. This is what we have discussed about that in our paper already. And also, we have some people working on these satellites. The people, this is the group of this one. And also, we need some theoretical research and data analysis. We have already a group here. And this Professor Jianwei Mei, they have already been here. And we hope some people to join this group because the data analysis is very, very important also. We have other teams in China. Here is some red star. They have some contribution for this TianQin space mission also. Recently, some progress have been achieved with this project. The payload research base and ground emulation facility, and also some flight experiment have been performed. This is our campus in Zhuhai, near Macau. Here is the building will be used in the next year. This is for the payload research, and we also need a cave laboratory because there is very stable. And also we need a laser range station because our system will be help us to formulation the satellite constellation. And this is the picture. This is a cave laboratory, and this is a station, this range station. And this is our campus. This is on the contraction. You see everywhere are contraction sites. Then near the South China here, and here is our TianQin research building. This is a cave laboratory, and here, just here is the laser range station there. And also the ground emulation facility, which will be contracted in our Shenzhen campus there. This proposal has been approved by the Shenzhen local government. We get a big grant to support this one. Here is some design about this facility, the construction about that. And last, we have a flight experiments. This, the Chang'e 4 have been launched very recently, and this ray-line satellites have a Rachel, called cubic Rachel reflector, which have been launched. This one. And also, this is some design about our TianQin 1, TianQin First, will be launched next year, where we will test the Dragfree technology and also the inertial sensor, check the sensitivity of inertial sensor, and also the space-borne laser interferometer, something like that. And we want to find some cooperation. We have already two very good basement. First one is in our host in Wuhan, Huazhong University of Science and Technology. The second one in our Shenzhen University here in Zhuhai campus. We have already two very big group. And also, we have already held 4 symposiums since 2014. And we just stopped this last year because we have some competition with our Chinese Academy of Science. There are another group trying to propose another Taiji mission, space mission, just like that. So this is some story about that. Nevertheless, we want to cooperate with our international college. The first one is at the government level, such as we have already have a government level cooperation with Russia. And also we want to have an institution level with some university or some research institute. And also we also welcome to have some cooperation with our colleges, the group or personally, something like that. So the final remark, TianQin is grows stronger every day. So you will find some indicator about that. And the second one, we welcome all forms of international cooperation with our colleges, not only here, but everywhere in the world. So this is a campus. The left one is Zhuhai campus. This is our Shenzhen campus. Two of them are two are very new one. And this is some advancement. The last night we have given this introduction. So I hope every people can go there. Thank you very much.
Thank you. Questions, Anna?
Yeah, Anna. Yeah.
Thank you. June, can you tell us something about the microtrusters? At what level? I mean, how long would the mission in space last due to the propellant? Do you have microtrusters? I saw that they are developed in Beijing, which are low noise but also high specific impulse to allow low quantity of propellant and the mission to last long in space.
Thank you. And I'm so missing with you, and because I sometimes get some message, email from you, but I can't remember reply for your answer sometimes. I will meet you PSI University next year, tomorrow, sorry. So the first question is that the lifetime of this space mission is about 5 years. So the second one, the microthruster is on the researchers, not only in Beijing, but also in my laboratory already. So we try. We have already have a space test in the mini Newton thruster, but not yet macro Newton thruster. Yeah.
So suppose we are both lucky and we get up together.
Yeah.
What kind of science could the two missions do together? Is there anybody working to the case of having this mission and LISA up together?
Yeah, this is I think my first motivation about that. The first motivation, we want to test general relativity because this was proposed before that. The second one, I hope to catch your time schedule. If we can catch that, the one is near our Earth's orbit, another is one far away. So we can comparatively, we can verify each other the signal, what we have get. We have asked my group to start to do such research. Yeah, already. Yeah.
Okay. Combine the different orbit-oriented LISA and TianQin result. I would expect the systematic error in data analysis would be reduced.
Yeah, right now I cannot exactly reply your question, but you see, what my experience is that once we get additional information about something, we can increase the confidence about that. So sometimes we talk about what is the confidence of your result. The result in sometimes we can 68%. The 1 sigma confidence or 2 sigma confidence, something like that. Once the signal have been captured by the LISA and also captured by our system, so we can compare it. Just like the LIGO signal have been verified by the Virgo project. That is the most important things, I think. But we don't know how big factor can be improved. Right now, I don't know. Yeah, good question.
Further questions? I see no further questions. Then we thank you again.
Thank you.